About the project submission, right? So some of you already submitted, and you have until next Tuesday, if you want to take advantage of the extension. How about the exam? How was the exam? Okay. Good. So the homework is being graded. They'll return that, and then the exam sometime after that. And then I'll start putting the homework problems for the new things we started doing. In fact, the planning graph one is already going to be part of the next homework, so you can start doing that. So before I start, are there any questions? So, so we were doing, basically the last, we were talking about planning, which is essentially search when you have propositional representations of state. That means the state is made of state variables, which can be true or false. And then you have actions that modify their truth falsity values, right? So one thing that you might want to ask yourself is, remember the blocks word, which we used as an example, right? One interesting thing was that if you have, let's say, stack AB action, right? You had to say one of its effects would be on AB. But you also had to say that it would delete clear B. Right? That looks like an overkill. Isn't it obvious that if you have something on top, if there's something else on top of that block, then that block won't be clear, right? In fact, basically the way we had was you had, if you don't do this, if you don't write this, then our semantics was that you start with the state and you essentially only change the variables that this guy is mentioning and then copy over everything else. And so if you did not write not clear B here, then you are likely to keep clear B around, even though you have on AB. And that wouldn't be a complete, correct state. That's the reason we were dealing with it that way. But a different way of looking at the world would be, that we essentially acted, while the actions were changing, taking you from one state to another state, we still acted as if the state variables in a given state are all independent, as if they were getting their truth and falsity values independently. But that's not true. Okay? If certain variables have value true, then certain other variables cannot have value false, for example. Okay? And vice versa. And so when you have state variables on AB and clear B, these are state variables, you cannot have any real state where on AB is true and clear B is true. It's impossible. And basically, the way we understand this, commonsensically, the way we understand this is we have a kind of a rule in our head saying that, if some block is on top of B, then B is not clear. So in some sense, I will, write this notation. I'll write this on AB implies not clear B. Okay, this is implication sign. We'll talk about it in a minute. But you have a rule like this, that whenever there's on AB, then B is not clear. Okay, and once I have this rule, then I can essentially, as soon as I write on AB, I would myself be able to realize that clear B is not true. You see what I'm saying? So we could reason about, in fact, what happens in real world is you know the values of some of the state variables. Okay, you perceive them, let's say, you sense the values of some of the state variables. And then there is knowledge that you have about the world, which allows you to infer that certain other state variables have certain other values. Okay, until now we didn't do it that way because first of all, we assumed in the normal search model, we assumed that the states are atomic. If the states are atomic, there is no state variables. And then we went from atomic states to states with state variables, but we acted, in a sense, without realizing, we acted as if they were all completely independent. So, but for this bad action, okay, which essentially seems to be changing the values, in sets at a time, all variables can have, each variable can have any which value it wanted. That's the sort of assumption we had in the back of our head. But the reality is you actually have, additional knowledge which will allow you to sometimes say that variables are connected. There are constraints between the valuations of the variables, state variables. And if you can represent these constraints, then you should be able to actually use them and infer, given I know this and this is true in the world I live in, is the following state variable true? In general, given that I know the following facts are true about my world, is this additional fact true or false? Okay, that is the kind of reasoning that we will start talking about today. Okay, so you start talking about representing the state information and any rules that you know. And then once I represent it, is there a way in which I can combine this rule with what I know and realize that clear B must be false? Okay, so that's a way of connecting, you could have come to this particular chapter, propositional logic, in any which way. In the text, actually, they went from atomic states to propositional logic directly. Okay, we went from atomic states to state variable-based states, which is planning, and then we are coming to propositional logic. And one motivation for that is now after this, you can actually be able to start talking about reasoning about the structure of the state itself. Okay, so that's just the way to segue into this particular chapter. Okay. Anyway, so this is a particular kind of logic. So in general, whenever you represent what you know about the world, and then you want to infer what else is true, given what I know, what else is true. That's a logic. A logic tells you basically, given what you know, what else is going to be true. Okay? There are different kinds of logics. We will talk about the simplest kind of logic in today's class, which is propositional logic. Okay? In understanding propositional logic, you understand most of the interesting building blocks of any knowledge representation scheme, which is first you need a way of writing the sentences, you need a syntax. Okay? And then you need a way of combining sentences to infer new sentences. I first of all use the word infer. Okay, infer new sentences. Now, and whenever I infer new sentences, it better be the case that the sentences that are inferred are done in some principled fashion. Okay, and obviously sometimes that you can infer random things and then that's what is happening in this particular example. So essentially, if you go through this, they are using some logic to come to a conclusion. Most of us don't think that is a well-founded logic. So the question then is, what should be true in well-founded logics? When is an inference considered a reasonable inference? Okay, so we will talk about the notion of entailment and computing the entailment using inference rules. And we figured, once we understand that in the propositional logic, then we basically use the same ideas in other types of logics. One other logic we'll talk about in this class is first-order logic. The third kind of logic we'll talk about in this class is propositional probabilistic logic. Okay, so In some sense, propositional logic itself, all of you know. Boolean algebra, how many of you know Boolean algebra? Boolean algebra is propositional logic. Okay, so I'm just going to talk about what you know already. Except I will talk about it with a slightly different twist. I mean, you look at the same thing that you know, but you look at it from a different point of view. You think of Boolean algebra as a representation language. And you understand what are its inference rules, and when do you say that an inference rule is sound and complete. These are properties you'll understand. Okay, and then we'll also understand as part of this discussion that if you think of Boolean algebra or propositional logic, which is one and the same, as one type of logic, then what's the spectrum of logics that you can have? And then I already told you two other points in the spectrum I'll talk about, which is first order logic and propositional probabilistic logic. But you kind of want to get a feel for why did this come up? Why are these 3 points not there? Okay, so those are the things that you'll understand today. Any questions? Okay. So basically, this is sort of an abstract discussion of why you want to understand knowledge representation. The essential idea is you want to sort of throw in whatever a knowledge, representation language has. Basically, you are talking about knowledge base in which you write what you know, and then there is some inference engine that works on, what you write, and then comes up with new inferences. Okay, which are basically essentially as if you have some sentences here, the inference engine works on those sentences and comes up with new sentences. Those are not present originally, but they may as well be present. Do you understand what I'm saying? So if I told you, my knowledge base already has RAB implies not clear B, and has one more sentence saying unab, then I may as well have written another sentence saying not clear B. I don't have to, because implicitly I have written it. The beauty here is implicit. That means that the point here is that I get to write what I know about the world in a compact form, and many more things are true about the world, and they can be derived as and when needed. Okay, and so that's what a knowledge representation scheme will tell you. And so it's some sort of, the word declarative means you write down what you know, not as a procedure, but as a fact, okay, or an axiom. And then the agent essentially writes down, if you're thinking in terms of an agent architecture, this agent is going to write down what it knows about the world in this particular logical language. And then it asks itself, given what I know, what must I do now? Okay? And as part of that, what I know, if I know this, then I also know these other things implicitly. And if all these are known, then this must be the action that I should be doing. So that's in essence how its reasoning will proceed. Okay. So a knowledge-based agent should be able to represent things. It needs to represent states. It needs to represent actions. It needs to represent knowledge about the states. Okay. And it should be able to throw in additional things. If I tell you a new sentence, you should be able to throw that sentence in. Okay? And then you should be able to update representations whenever it learns new things, whenever it's been told new things. It should be able to deduce properties of the word. Okay? Even if I don't tell you that B is not clear, I only told you on a B, but you can then deduce that clear B is false. That's what you do, okay? And then as part of that, you will also be able to deduce appropriate actions, So that's what a knowledge-based agent will do. And for knowledge-based agent to work, it basically are essentially, in all these pieces, I'm basically saying either represent what you know or infer some properties given what you already know, okay? So knowledge representation is representation plus reasoning. So logics are essentially formal languages for representing information. You have some syntax and you have some semantics for the syntax. Okay. So for example, language of arithmetic, x plus 2 greater than or equal to y is a sentence. It's syntactically correct. x2 plus y greater than is not a sentence. It's syntactically not correct. Okay? Just because a sentence is syntactically correct doesn't necessarily mean that it is true. It's just a sentence. Okay? And you want to know whether or not it is true. That is basically the reasoning aspect. Okay? So x plus 2 greater than or equal to y is true if and only if the number x plus 2 is not less than the number y. That's sort of what you have in your mind as the semantics of this particular statement. Okay? And another interesting thing about this sentence is that if I say x plus 2, then you are essentially thinking about different worlds where x can take different values. World 1, x takes value 1. World 2, x takes value 1.1. World 3, x takes value 1.4. World 4, x takes value 7.9. In this particular case, how many worlds are there? Infinite number of worlds. Right? Now, the question then is x plus 2 greater than or equal to y. This is, and so in each of these worlds, I'm sorry, actually, we actually have both values x and y. So really, in thinking about this particular statement, x plus 2 greater than or equal to y, one useful way to think about it is, as far as you are concerned, world is made up of valuations for x and y. Okay? Here is world 1, where x equal to 1, y equal to 3. Okay? Here is world 2, x equal to 4, y equal to 10. Here is world 3, x equal to 0, y equal to square root of 145. These are 3 words. Okay? Now, when your understanding of arithmetic is that this particular statement is it true in this world? Right? Because 1 plus 2, 3 is greater than or equal to 3. It is true in this world. Okay? What is it true in this world? 4 plus 2, 6. 6 is not greater than or equal to 10. So this world, this statement is not true in this world. This statement is true here, it's not true here. Okay? And finally, how about this? Not, right? 0 plus, so 2 is greater than or equal to square root of 1.5, that's also true. So what's interesting actually is if you were to enumerate all the worlds, we have infinite number of them in this particular case. In fact, you have essentially x and y, plane. Every point in the xy plane is a world. Okay? And then some worlds, in some of the worlds this statement is true, some of the worlds this statement is false. In particular, since you know some math, that essentially there is a line that separates the good worlds from the bad worlds. Everything above, on and above that world, on that line, and above that line would be good worlds, everything else will be bad worlds. Okay? So really, what the semantics of a statement here, arithmetic relation, is the set of the words in which that statement is true. That's what a semantics is. This is a useful thing to understand because when we come to propositional logic, that's the same question. If I tell you an extra sentence that is true, that reduces the number of words you could possibly be in. Think of 20 questions, the game. You're trying to figure out, I have something in my mind. You're trying to figure out what that is. And you get to ask questions. Before you asked any question at all, basically what's in my mind? Well, it could be anything. Okay, after the first question, you ask, is it a, a live thing or a dead thing? I mean, is it alive or not? Is it live or not? And I say, no, it's not live. Then you know that a whole bunch of possibilities are removed now. As you know more knowledge, you cut down the number of worlds you could possibly be in. Having complete knowledge essentially means you know exactly the world you are in. You can have a little more than complete knowledge, which means you actually with what you know, there is no world that is consistent with what you know. Did I lose you or not? Okay, so as I keep telling you facts, right? As I keep telling you facts, in the beginning you think that you could be in any one of the possible worlds, a large number of possible worlds. As I keep telling you more and more, the number of worlds keeps reducing. If you're lucky, I'll reduce it to exactly one. That means you know exactly the world you are in. If you're unlucky, you might pass that and become exactly 0. That means there are no worlds in which whatever I said is altogether true. Do you see what I'm saying? Now, as I'm telling you, I am increasing the size of your knowledge base. Your knowledge base has more and more sentences. This knowledge base corresponds to some set of words. Okay? The set of words that you have keeps reducing as I keep adding more knowledge. If the set of words becomes 0, that means your knowledge base is inconsistent. That means there is no world that's consistent with everything that you know. Okay? And this is important because, and all of this comes from the semantic view I'm telling you, which is for every logic there is a notion of worlds that makes sense for that logic. For arithmetic, the notion of worlds would be the valuations for the variables, the real number values for those variables. Okay? And then under that, then you basically know how to compute whether or not this statement is true in a given world. That's what the rules of arithmetic tell you. Once you know that, then essentially you know, in this case of these 3 worlds, this is a valid world, and in fact, a valid world is called a model. The first piece of jargon, you should remember. In any logic, if I give you a set of sentences and I give you a world where the conjunction of these sentences is true, that means this world satisfies all those sentences, then that world is a model for this. Okay? Typically, you have many models. That means what you know is consistent with many, many worlds. But as you keep knowing more and more about the world you live in, you reduce the number of possibilities. But sometimes you can overshoot and you get inconsistent information, in which case you reduce the number of words you know to 0. That means, in fact, you learned inconsistent information, so it can't possibly be true. Okay? And the fact that as I keep adding knowledge, your words, the number of words that are consistent with the knowledge keeps monotonically reducing, that is actually a very important property of certain types of logics. This is called monotonic logics. Okay? And mostly the ones that we talk about in the beginning, they have that property. As you know more, you reduce the number of possibilities. Okay? So this is arithmetic logic. We won't talk about it, but we'll talk mostly about, this, as I said, propositional logic, first order logic, and so on. And in understanding these logics, it's worth asking about 2 different questions about what those logics commit about the worlds they are trying to model. Okay? One commitment, again, this is another jargon, ontological commitment. What does this logic say the world is made up of? In effect. Okay? For example, propositional logic says that the world you are trying to model is made up of primitive sentences that are either true or false. Those sentences are propositions. Okay? So propositional logic says world is made up of propositions. It's great for us, that's what you're actually trying to model. Okay? But then your world is not just made up of sentences that are either true or false. In fact, you might say that my world has more structure. Actually, atomic, when you were in the atomic representations, you thought world is made up of atomic states. Okay? When you came to propositional logic, you said world is made up of propositions that are either true or false. But your world has more structure than that. You actually live in a world where there are objects, this guy, this table, this thing, and the relations between objects. Okay? If you do that, if you say that, then you have first order logic. First order logic assumes that the world is not made up of just propositions, but it is made up of objects and the relations between them. And every higher level logic can be compiled down to the lower level one. So if you believe that you are actually in a world where there are two blocks and they can have on relation between them or clear relation on each of them, that can be converted down into propositional representation where you have propositions on AB, on BA, on AA, on BB, clear A, clear B. They can be true or false. And that whole thing can be converted down into atomic representations. You see what I'm saying? So one way you are admitting there is more structure to the world. The other way you are assuming the world is just atomic. Okay. So propositional logic makes ontological commitment that the world is made up of propositions. First order logics make, okay, here, look at this scheme here. World is made up of facts which are true or false. Our first order logic assumes that world is made up of both facts and objects and relations between them. Okay? Those are 2 points at least. Now the other dimension for a logic is what state of knowledge do you have? Okay? In the case of propositional logic, something is either true or false. Okay? More interestingly, so that in any given world, you essentially would say the statement is either true or false. That you can understand. Okay? If I think I can be in one of the worlds, W1 or W2 or W3, and the sentence is true in W1 and W2, but not true in W3, then you can neither say this sentence is true, nor say that this sentence is false. Do you understand what I'm saying? I have a friend. Okay, I have a friend. Does my friend have legs? Probably yes. Actually, most of will say yeah, yes. Okay. Does my friend wear skirts? Maybe yes, maybe no. Given the knowledge you have, you don't know. So you can neither say yes nor say no. Okay, now what's interesting actually is in this example I gave you, I have a friend, does my friend have legs? In fact, that too is maybe yes, maybe no. I mean, by the looks of me, you don't know that I am actually actively avoiding people who don't have legs, right? So it's possible that I have friends who don't have legs. You can't be completely sure. Okay, but even if you just count the possible number of people I can be friends with, the number of people without legs, in Tempe area is much fewer. So the likelihood that my friend doesn't have legs is much lower. Whereas the likelihood that my friend wears a skirt or not is 50-50%, because Tempe is made up of 50% men, 50% women. Okay, and normal logic can't differentiate between these two. It basically would say, well, I can't say about the legs, I can't say about the skirt. If you want to talk about degrees of belief, which is probabilistic logic, it will say that, yes, in fact, in the first case, 99% certain that your friend has legs, and only 50% certain that your friend is wearing skirts. And only 0.01% certain that your friend speaks Swahili. Okay, do you see what I'm saying? Whereas if you're going with the, so basically if you assume that the world is made up of, propositional logic assumes the world is made up of true, false, and unknown. The unknown is essentially, if I just tell you I have a friend, you don't know whether they have legs or not. And you also don't know whether they're wearing skirts or not. Even though one of them is more likely than other. You don't differentiate between your states of non-knowledge. Okay? If you know for sure, it's yes. If you know for sure that negation is true, it's no. Everything else is unknown. Okay? So is first order logic. It also takes true, false, unknown. Whereas probability theory allows degrees of belief. Probabilistic logics allow degrees of belief. The unknown is also 1 and 0, and everything else is unknown in terms of a probabilistic point of view. Whereas a probabilistic logic can allow you to say 0.7, 0.7057. Okay? So that's your propositional logic is here, in this x-axis, epistemological commitment. Here is true, false, unknown. Here is degrees of belief. Now if I take this point, which is assuming true, false, unknown, and assuming that the worlds are made up of facts, that's your propositional logic. If you come here, that's your propositional probabilistic logic. If you go from here up, it's first order logic. So you're still assuming that the world is made up of true, false, and unknown, but you assume that it's also made up of objects and relations. And then finally, if you come there, that's first order probabilistic logic. Okay? And so that's the same thing that so you can start, we will start with propositional logic in today's class. Okay? And then having understood that, I can extend, for example, propositional logic directly with objects and relations. Then I'll get first order logic. Or I can say, no, I'll leave that commitment alone. That means I'll still continue to assume that my commitment is that things are made up, things are either true or false. The world is made up of facts. But I'll assume that my knowledge would be degree of belief. Not true, false, unknown, but degree of belief. In which case I get to talk about propositional probabilistic logic. Okay? And then having come here, I can essentially now throw in degree of belief. Or I can come here and throw in objects and relations. Either which way I'll come to first order probabilistic logic. Okay? The one interesting thing in this picture is this. Okay? Which is degree of truth. That is, given a specific world, in all these logics, given a specific world, a statement is either true or false in that world. The degrees come only because you have a bucket of worlds. If 90% of the worlds it is true, 10% is not true, it's then 0.9 probable. Or from the first order logic point, from the propositional logic point of view, its status is unknown. Because in some cases it's true, some cases it's false, so its status is unknown. But in any given world, it's either true or false. So the word fuzzy logic, you guys heard about fuzzy logic. And you must have heard of fuzzy logic, just while passing by, right? The interesting thing is in fuzzy logic, the assumption is that even in a given single world, the truth can be between 0 and 1. Okay, the best example I have for this, I think that's the one actually I believe your textbook also has, is, if you have, let's say, a set of, red puppies and brown puppies in a bucket, right? And then I close my eyes and pick up a puppy. I haven't yet opened my eyes. Is it red? It's either yes or no. Brown, either yes or no, no in between. Once I open, I'll know what the color is. But even before opening, I know that it's, each of the questions will have either yes or no answer. no in-between answer for a given puppy. Whereas in the bucket, maybe 90% of the puppies are red and 10% of the puppies are brown. And so, in fact, in the bucket, the red, that a puppy is red has degree of belief 0.9. That's what this entire set of logics deal with. When you come to fuzzy logic, essentially, you picked a specific puppy. And I ask you, is it red? You open your eyes, you still can't tell. It could be between red and brown. Why? Presumably because there was actually, not only did you have red puppies and brown puppies, they probably started breeding and changing color. So then individual puppies themselves now have colors between brown and red. Do you see what I'm saying? So that's basically what happens. So it's in some sense, one way of thinking about fuzzy logic is that the number of values for a state variable is either true or false in all these scenarios. Here it's multiple values. And the values are sort of somehow ordered between 0 and 1. Okay? So that's the fuzzy logic. We would actually not talk much about fuzzy logic at all in this course, other than probably to say at some point of time that it's kind of a bad logic, in the sense, the normal treatment for fuzzy logic has a lot of inconsistencies built in. At some point of time, I'll point that out. Okay. But it's useful to understand the big picture for logics. Any questions on this topic? Okay, so now this is a picture. Now you can actually see why we are starting from here, because if you start from here, you can either go this way or go this way. Get from. And in fact, as of today, when I'm speaking right now, I haven't yet figured out whether this year I'm going to do this way first or this way first. I've done both ways in different classes. Okay, if I go this way right after propositional logic, I will talk about propositional probabilistic logic, which allows you to talk about Bayes networks, which you may have heard of. Okay, if I go this way, then I talk about first order logic. The interesting thing is I would for sure not talk about this, because the first order probabilistic logics are beyond the scope of 471 right now. We still don't have enough of an understanding to teach it at 471. Okay, so that's where the reality is. Any questions? Okay, fine. So this picture, now I'm going to talk a little more about just the notions of entailment, which is basically sort of central to all these logics, and this is connected to this the idea that I pointed out earlier, that if I give you a knowledge base is just a conjunction of sentences in some logic. Conjunction of sentences in some logic. I told you something, I tell you something more, I told you something more. So now you have three things in your knowledge base. They're three together. So it's a conjunction of these three things. Now this knowledge base corresponds to some set of worlds which are its models. That means all these worlds, all these sentences are holding in all these worlds. Any other world, these sentences, some of these sentences are not holding. Okay? So the meaning of your knowledge base is the set of the worlds where the knowledge base is true. As redundant as this definition looks, it's actually a very important idea. That's the denotation. There's this notion of notation and denotation. Okay? Notation is the set of sentences that you have just notated, you wrote down. And its denotation, or the semantics, is the set of words in which those sentences are holding. Now, given this, you can basically talk about, if I tell you that I have a knowledge base and I want to know whether a particular sentence alpha holds in given what I know. I didn't specifically write alpha in my list of sentences, but maybe it already holds. So for example, my knowledge base said on AB, and whenever you have on AB, not clear B. So it didn't directly say not clear B. And yet you know not clear B is true. Right? It's implicitly said. Given what you know, it's implicitly true, right? So the question is, I'm always asking myself, knowing what I know, is alpha true? And that question can be asked this way. If I know something, then I know I'm in some set of worlds where that knowledge is true, knowledge base holds. If in each of those worlds alpha is also true, then alpha is entailed. That's it. Okay? So it's in terms of the models of the alpha and models of the knowledge base. So let's say you have a knowledge base which is a set of sentences, and suppose this little set here of worlds is the exact set of worlds in which this knowledge base holds. Suppose this is the set of worlds where alpha holds. Okay, then is alpha true? Knowing that you are, if you know that KB is true, that means you know these are the sentences you know are true in the world you live in. So you haven't yet figured out which world you live in, you have narrowed it down to this set of worlds. You can say alpha is true if in all of those worlds alpha is still true, right? Right? Okay? So for example, I said, I have a friend. And then right now the friend is walking to 7-Eleven. Do you know who my friend is? Do you know what shirt he or she is wearing? Do you know whether my friend is alive? Yes. Again, unless you see dead men walking or dead women walking, you know that my friend is alive because I just said my friend was walking to 7-Eleven. Using all your background knowledge, you figured out that my friend is alive. You could be, right now, my friend could be anybody. Could be wearing any shirt, any pants, or none at all. Right? And yet you know that they are for sure alive. That's the power of inference. You know, it's very easy to say, I still don't know which world I am in, so until I know exactly who your friend is, I'm not going to commit. That way you would basically be very slow in reasoning. Do you understand what I'm saying? So that's what happened. So when I said I have a friend and my friend is walking to 7-Eleven, you have all these possibilities of friends, you know. Tom, who is alive, Mary, who is alive, John, who is alive, and here is Smith, who recently died. Right? Right? These are all possibly the friends I'm talking about. This cannot be one of my friends, for example. Now, if it turns out that every friend of mine I can still be talking about is alive, then my friend is alive. And that's just a set subset relation. So I'm saying the models of alpha are a superset of models of the knowledge base. Then alpha is entailed by the knowledge base. Fine? Okay? So this is what we do in computing. All logics do, you know, is basically just computing this relationship. That's all. They're just checking whether the worlds for the knowledge base are a subset of the worlds for which that you're trying to prove. The words for the sentence that you're trying to prove is true or false. Okay. Now the interesting question, of course, is this. I mean, I have shown you a picture there. There clearly alpha is true, right? I mean, so in this particular case, KB entails alpha. Yes. Here is another picture. This is KB. This is MKB. This is M alpha. Now, in this world, does KB entail alpha? Does KB entail not alpha?
Yes.
You learned something. How about in this world, KB entails alpha? Yes. Does KB entail not alpha? No. Here, this, no, this, yes. About this picture. Okay? Just before this.
No.
Is MKB entailing alpha?
No.
No. Is MKB entailing not alpha?
No.
No. That's the part about unknown. Do you see what I'm saying? Even though in any given world, law of excluded middle holds, if it's not true, then it must be false. If it's not false, it must be true. But given a set of worlds, excluded middle doesn't hold. So there are worlds where it is true, there are worlds where it's false, and so clearly it's unknown. Its entailment status is unknown. So in this case, obviously, if you have some sense, you'd like to say, it's almost true. If you randomly, if all these worlds have equal probability, then the probability that you would be unlucky enough to be in one of these worlds, where alpha would be not true, is very small. So in fact, you're more likely than not that this has high probability of entailment and this has low probability of entailment. But normal logics don't differentiate. You have one, mixed case, you're dead, you're unknown. Do you understand what I'm saying? Okay? Okay. So that's basically the notion of entailment and understanding it in terms of the sets of words. Okay. And it's all of, when I say inference, computing, a knowledge, you have a knowledge base and you have an inference engine which looks at what is written in the knowledge base and tries to infer new sentences. What it's doing is, it's guessing an alpha and checking whether alpha is entailed or not. And in essence, for that, it needs to compute the set of worlds where alpha is true, and set of worlds the knowledge base is true, and check whether the subset, superset, subset relation holds between them. If not, it's not. So you remove the magic in inference, in essence. Okay? However, there are too many words. Okay? So the question is, these pictures, you don't get to normally draw the Venn diagrams. You want to be able to do this more efficiently. That's what we are here for. Okay? So there are two ways of efficiently proving things without having to draw Venn diagrams. One idea is basically kind of enumerate the models and convince yourself that every model of the knowledge base is also a model of alpha. Is the vice versa needed? Must it also be the case that every model of alpha be a model of the knowledge base? No. All you need is every model of the knowledge base must be also a model of the alpha. In fact, for propositional logic, we'll call this the truth table method. Essentially, you would write big truth tables where the entire knowledge base evaluates to true, and in those rows, you check if the sentence you want to prove is also true. If it is true in those rows, then it is entailed. We'll get to that in a minute. Okay? And if you do that, that's called model-based entailment computation. Okay? The other way of doing it is essentially come up with some syntactic rules which will allow you to automatically write new sentences given sentences that you have. Okay, for example, for propositional logic, I can give you a sentence, a syntactic rule which says whenever you have something like A implies B and you have A in your knowledge base, you get to go ahead and write B into your knowledge base. And this actually has been given a name. It's called models ponens. It's a particular inference rule. Okay, now the interesting things about these inference rules is if you write an inference rule, you want to make sure that whatever the inference rule says is also true by ultimately this method. Because this is the definition of entailment. And model checking computes this directly, more or less. So to say that an inference rule is good, you are asking whether there are two things that you can ask. If the inference rule says this sentence is true, that if the inference rule says that this sentence is entailed, is it also entailed by the model theory? And secondly, for every sentence that is entailed in the model theory, is the inference rule going to be able to say that it is going to be entailed? Did you get what I'm saying? So this way of computing entailment is the right way. Okay, this is like the fx plus h minus fx divided by h tends to 0 definition of derivative. When in doubt, ultimately all proofs have to go back to that. Right? This is ultimately the notion of entailment. Now I want to find a shortcut for entailment, which is like the syntactic rule. Now I can make up random syntactic rules. Here is another syntactic rule, by the way. A implies B, B, A. This is actually called abduction. Okay? Now, what's the difference between these two rules? One of the interesting things is this rule has the property that if this rule allows you to say a sentence is true, a sentence is entailed, then it actually is guaranteed to be entailed by this method. That's not true here. Okay, if A is true, then B will be true. B is true. Doesn't necessarily mean A is true. Somebody else could have caused B. Do you see what I'm saying? So this is not always true. So this is a between this rule and this rule, you talk about a property called soundness. The soundness essentially means an inference rule is sound if, whenever it says that a fact is entailed, it is actually truly entailed. And an inference rule is complete if, for every fact that is truly entailed, this inference rule will allow you to figure that out just using this rule. If you have both sound and complete, then the inference rule is able to compute the entailment directly. No more and no less. This is sort of like saying all truth and nothing but the truth. Okay? Soundness, so when you go to the court and they when you are about to give evidence, they'll ask you to take this oath, right? And the oath says that I will say all truth and nothing but the truth. Okay, which part is which? Soundness is all truth or nothing but the truth? Soundness is all truth or nothing but the truth? Say it loud. Which possible witness can tell all truth? When there's truth about quantum mechanics, a random person who goes to Tempe Municipal Court will know that truth? In fact, they went to Tempe Municipal Court because they have no classes to begin with. So they probably don't even know quantum mechanics exists. Nobody can tell all truth. Okay, so it's a nothing but the truth that's even more important, actually. So nothing but the truth is essentially soundness. If you are allowed to say things that are not even true by the entailment procedure, then you are an unsound inference procedure. Modus ponens is a sound inference rule. Abduction is not a sound inference rule. Turns out neither of them are complete. Turns out that if you just keep using model exponents, you will not be able to prove some sentences that are actually entailed. Okay, so it's a sound but incomplete inference rule. And part of what we'll find out is this nice little rule called resolution rule, which some of you probably know, but many of you haven't heard of, which actually has the property that it's both sound and complete. That means everything that is actually provable can be proved using just resolution. And if the resolution says something is true, it is actually true, even if you did it the first principles way. For logics, first principles way is model-based. Okay? So that's basically the notion of inference rules. So you can either do it by model checking or inference rules. And inference rules, if you're talking about inference rules, you need to think about soundness and completeness. Okay? Now, finally, with this in the background, we will sort of zip through propositional logic. Okay, ready? If you remember propositional logic, I'm just basically making you look at it in the, with the background of all this jargon that we just developed. Okay, so for the propositional logic, you need a syntax. So you have propositional symbols, any symbol, is a propositional symbol, and then you make sentences using propositional symbols. And sentences are defined recursively this way. If S is a sentence, every proposition symbol is a sentence by itself. Okay, that sentence corresponds to yes, this proposition is true. That's what that sentence is. Okay, if S is a sentence, negation of S is also a sentence. Okay, and if S1 and S2, if S1 is a sentence and S2 is a sentence, S1 conjunction S2 is a sentence. If S1 is a sentence, S2 is a sentence, S1 disjunction S2 is a sentence. And if S1 is a sentence, S2 is a sentence, S1 implies S2 is a sentence. And in fact, and then also if S1 is a sentence, S2 is a sentence, S1 if and only if S2 is a sentence. And of all these, it turns out that the implication and the two-sided implication are actually not primitives because they can be written in terms of the other sentence. So if I ever write P1 implies P2, in logic, in propositional logic, it's actually equivalent to not P1 or P2. That's what it is. That's the definition, basically. Okay? And when I say these two sentences are equal, that means the set of words where this sentence holds is one and the same as the set of words where this sentence holds. So as far as you're concerned, there's no difference between them. Okay? And of course, obviously, P1 if and only if P2, by the way, I don't know if you noticed, the implication sign can be written this way or that way. And both are considered equal. And similarly, the negation can be written this way or that way. It's just by convention. Either of them are fine. Okay? So if you have double implication, since a single implication can be written this way, double implication is nothing but P1 implies P2 and P2 implies P1. So that's nothing but not P1 or P2 and not P2. So you keep this in mind that implication symbol is what they call syntactic sugar. You can remove it. You can go back to just conjunctions, disjunctions, and negations eventually. And if you can understand things in terms of conjunctions, disjunctions, and implications, then you understand everything because implications can be compiled away. Okay? Now the semantics. Semantics essentially are in terms of the computing, given a sentence, given any arbitrary propositional logic sentence, and given a world, you should be able to tell whether the sentence is true in that world. Now the question is, for the arithmetic formulas, remember x plus 2 greater than or equal to y, what's a world? World must give the values to x and y. Similarly, for propositional formulas, the world would be something that gives truth-false valuations to each of the propositional symbols. That's what it is. If I have a propositional sentence with 3 propositions, then in essence, I'm talking about 2 power 3 words. Okay? And in each of these words, I should be able to tell whether this sentence is true or false. Now, if I have a sentence that is true in all the words, it's called a tautology. And you can put down your friends and also be seen as a geek by saying, stop talking in tautologies. Because tautology is saying something that's always true. You never give any information to somebody by telling them something that's always true. So for example, I have a friend. First question, I told you first, okay? The second, 1 plus 1 equal to 2. Do you know anything more about my friend? No. Because I told you something that's just true. Has nothing to do with my friend. Okay? Tautologies don't add any additional information. They're not removing any words because they're true in all the words. Whatever words you had before, you still have them. Okay? The opposite of tautology is an inconsistent sentence. I have a friend and pigs fly. What world am I living in right now? There is no world where I have a friend as well as pigs fly. Okay? So this is basically because, in essence, so again, going back to this, you're giving the truth-false valuation of a sentence in a given world using the propositional logic rules. And those are the familiar rules, you know, which is conjunction. You know, if P1 is true, P2 is true, P1 and P2 is true. If P1 is false, P2 is true, P1 and P2 is false, and so on. There's a truth table for AND. There's a truth table for OR. There's a truth table for negation. There's a truth table also for implication. And it turns out that the truth table for implication is the same as, you know, truth table for that. Okay? So this is how you compute, given any arbitrary propositional logic formula and a world, you can tell whether it is true or false in that world. There will never be I don't know. If I give you a propositional logic formula, very complex one, which is takes like a full long sentence, full long page, and a world, and you say I don't know, you don't get a badge. You just get called dumb, right? because you know, it's either true or false. There's no in between. In any given world, you know, any arbitrary formula is either true or false. There's no in between. And propositional logic rules tell you how to compute that. That's what truth tables are for. If on the other hand, I give you a propositional logic formula and I give you a set of words, you can say I don't know and you may be right. Because it may be that this propositional logic formula holds in this world, but doesn't hold in this world. So in that case, unknown is the status. Okay? So this is basically repeating what you know, right? Is there anything in this slide that is surprising to people? Okay, fine. Now, inference, I'm now going to do model-based inference. Remember the subsets inference that I was talking about? I can do this just by writing the truth tables directly. Okay? So here I have my knowledge base is A or C and B or not C. That's my knowledge base. So I've just been told that either A is true or C is true, or both are true. Because in logic, A or C means either A is true or C is true or both are true. Okay? And then B or not C. So this is true and this is true. This is what I know about the world I live in. My question is, can I then prove to myself that A or B is also true given what I know? This is kind of interesting, right? I mean, slightly more complicated. You may not have just right away able to see it. Okay? That's where we can do it automatically. So notice that since all of these are made up of just 3 propositions, A, B, and C, so my truth table essentially will have A, B, C, false, 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 true, blah, 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 8 different words. in each of the worlds, you should be able to write, the valuation for ARC, valuation for this, valuation for knowledge base, which is just the conjunction of these two, and valuation for alpha. Right? And then, in all the worlds where alpha is true are its alpha worlds. All the worlds where KB is true are the KB worlds. What you really want to see is if in every world where KB is true, alpha also is true. If so, it's entailed. Right? Okay? So, then, you can go through this slowly, but, you know Boolean algebra, so I'll do it fast and then you can go back and check. So, I do it fast by just going to the slide which shows ARC in this case would be false because A is false, B is false, C is false, so ARC must be false. Okay, and similarly, it's true here because A is true, and if one of them is true, this is true. And similarly, B or C, this is the values. And so, since the knowledge base is nothing but this and this, this part will be true only if both are true. So false, 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 true, true, false, true, true. Now, separately, alpha, remember what alpha is? Alpha is ARB. That, basically, you can also evaluate because you know the words. Alpha is false here, true here, true here, true here, true here, true here, true here. So you have all the information you needed. Right? So if you actually want to think of this as world 1, 2, 3, 4, 5, 6, 7, 8, then the words for the knowledge base, are so 1, 2, 3, 4, 5, 7, 8. That's the words for the knowledge base. Right? And what are the words for alpha? 2, 3, 4, 5, 6. Oh, I'm sorry. What did I say? 3, 4, 5, 6, 7, 8. Okay, so this is knowledge base. Alpha is 3, 4, 5, 6, 7, 8. So if I draw this Venn diagram, obviously this set is a superset of this set. You're done. So you just prove to yourself that alpha is holding. Every time KB is true, alpha is true. Do you see what I'm saying? Okay? So basically I'm just showing the one way of looking at that is only focus on the worlds where knowledge base is true. And check if in every one of those worlds alpha is also true. If in any of them alpha is not true, you know that it's not entailed. If in all of them, when it's true here, it's also true here, then it's entailed. Notice that it's also true somewhere else. But that doesn't matter. All I care about is whenever this is true, this is also true. Okay? Now, one interesting question is suppose my sentence is A and not A. My knowledge base is A and not A. Okay? My knowledge base is A and not A. Okay? And the sentence I want to prove, alpha, is, pigs fly. That's a proposition. Okay? So imagine that basically you have A and pigs fly are the propositions in your world. Okay? So the number of words, there are 4 words. Okay, there's A, pigs fly, false, 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 true, true, false, true, true. And the knowledge base, which is A and not A, would be false, 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 false. Pigs fly when they fly. There are worlds where pigs fly. The question I have is, now consider all the rows where the knowledge base is true. And make sure that in each of the rows where the knowledge base is true, alpha is true. I argue that yes, that is the case. Yes? Show me a row where knowledge base is true and alpha is not true. There is no such row. Right? So it's logically correct to say that if A and not A is true, pigs do fly. In particular, it just comes from the definition that from from inconsistency, you can derive anything to be true. It's just definition. So the moment your knowledge base becomes inconsistent, it's not that you implode. You now start saying everything is true. Because you have no words where you are true. So clearly everybody's truth, so the words where you are true, which is empty, everybody else is true too. So this is a funny fact about logic, that once your knowledge base becomes inconsistent, everything is provable. But it's not just made up fact, it comes directly from the set theoretic notion of the worlds in which knowledge base is true. As long as in every world where knowledge base is true, the fact that you want to prove is true, the fact is true. Okay? Right? So anyway, in this particular case, alpha is true in all the world's rows where knowledge base is true, so it is entailed. Okay? One thing I can do is, look, this looks fine, but you have to do, first of all, it's a pretty large truth table to write. If I have 15 propositions, I would need a truth table which has 2 power 15 rows, which would require a large paper. Okay? You want to basically somehow convert it. Not only that, after writing the truth table, you have to look into all the rows where the knowledge base is evaluating to true and check that alpha is not evaluating to not true. Right? I will shorten your life a little. Not shorten your life. Which I've been trying anyway, but I will shorten your work. I will shorten your work a little. Okay? I'll say, consider an extra column called KB and not alpha. KB and not alpha. I argue that must be always false if alpha is to be entailed. There is no case analysis anymore. Okay? So, if I have to add one more column which says KB and not alpha, and I evaluate it, and it becomes false, false, false everywhere, then alpha is true. So a way that you prove that alpha holds given what you know is to say that it's impossible for you to believe what you believe and not believe alpha, because there is no world where what you believe is true and alpha is not true. So if you choose to believe what you believe and also believe not alpha, then the number of worlds you have is empty. That's what is the reason why you must also believe alpha. Do you see what I'm saying? It's a consequence of what you know that alpha is true in all the worlds where you could be in. So, it's not possible for you to believe not alpha. Okay? Now, the beauty of this is, first of all, it's now much simpler, right? You just need to show that it's false everywhere. Secondly, and much more interestingly, and we'll come back to this next class, is we now converted this into what is called a Boolean satisfiability problem. How many of you have heard of Boolean satisfiability problems? Boolean satisfiability is a very simple problem. What we are saying is, if I have a knowledge base, KB, find me a model for the knowledge base. So I told you a bunch of sentences. Okay? Now, just give me a set of valuations for the propositions such that the knowledge base will evaluate to true. Just one. That's called Boolean satisfiability problem. Okay? And it's actually canonical computer science problem. The notion of NP completeness that many of you have heard of, hopefully, comes from the fact that the Boolean satisfiability is the first NP complete problem. And every other problem such that Boolean satisfiability can be reduced to that problem would also be NP complete. Because that other problem is at least as hard as Boolean satisfiability. Okay, it's a beautiful, canonical computer science problem. And it turns out also that Boolean satisfiability, it has lots and lots of uses. You know a large number of things that are true about your world. Take a guess as to what your world could be. Just guess one guess. And find one model. That's satisfiability. And what I'm trying to do is, and I told you that Boolean satisfiability, I just told you, is NP complete. Okay? This is Boolean satisfiability problem, except I'm asking you to say, I give you a set of constraints, I'm asking you to show that there is no model you can find for it. That's a conjugate problem. So prove to me that what I gave you, there is no world where everything is true. That's a conjugate problem. And that would actually be what's called co-NP complete. It's also kind of as hard as NP complete. I just proved to you that theorem proving, which is inference, is as hard as a Boolean satisfiability problem. And Boolean satisfiability is NP complete. So propositional inference is NP complete. So on that happy note, I'll let you go today. Okay? In the simplest logic you can come up with, finding whether or not something is true takes NP hard. It's an NP complete calculation.